thank you very much for the opportunity to be here again in Kobe and enjoy the environment and enjoy the workshop and the discussions here locally. So I would like to talk about future hard and software architectures for large-scale data assimilation and inversion. And what I would like to do is basically to talk on the needs and on the framework we are using this in. So there will be a heavy user perspective on the issue. I don't want to tell you how to do it. I just want to reflect on how we use supercomputers and what needs we see in an operational environment. And I thought to start with some pictures here. First of all, let me say I appreciate your approach to link your development to a number of key application areas. And the whole talk will be linked very much to a couple of them, really. Of course, one is here the NICAM LATICA-F type of application with weather forecasting and linking into climate simulations, reanalysis or monitoring of climate as well. But also, if you look into others like unstructured grids and computational sciences, this is all part, of course, of weather as well, and we are using unstructured grids. So it's also linking into work we do. And of course, the effort to use data and intertwine data with models is one of the key developments, which I will come to later, formulating some, what I call 3 critical success criteria for the supercomputer generations to come to be able to do this. So I think that the application which you are running here with Takemasa is developing on big data assimilation in a very short range forecast regime is a very important example, and come back to this later. So I've been here a couple of times. That was on an earlier meeting. And it's also linking to a lot of developments taking place in other parts of the world. So we are doing our development in a consortium of 8 countries in Europe, including Israel now, and Russia, Switzerland, Poland, Italy, Romania, Greece. Italy I named. So here, for example, we have a couple of discussions with the Swiss supercomputing people. And let me say, we are one of the only weather services who is running their weather model also on GPUs. It is used in several countries. And so I believe it's the only weather model running on a GPU supercomputer in Switzerland. And this is here the Cosmo E and the Cosmo 1. I will come back to this later as well, because it links into various things from Monte Carlo to uncertainty quantification and other issues which you have on your list here as well, if I look into number 9, for example. Okay, so what do I want to do? First of all, I want to show you a little bit about how we operate in an operational forecasting center, which might be a little bit different to a research type environment for a supercomputer. Some things are similar, some things are different. And I want to show you a little bit about forecasting. So this is like giving background to these criteria, which I have in my third part. And then I want to go further on to some ongoing research projects and development projects on nowcasting and NWTP and their integration at the end, giving you like an example or further perspectives. So Deutscher Wetterdienst, DWD, is the National Weather Service of Germany. And we are responsible for weather warnings and predictions for, first of all, Central Europe, for Germany, of course, but beyond that, via our customers and our industry, of course. So we do it locally, and here you see like Central Europe. And we do it as well globally for various reasons, because weather is global, and if you go to day 3, you need global forecasting. Otherwise, you are not able to do it properly. So here's just some pictures from our main location, headquarters in Offenbach, Frankfurt-Offenbach in Germany, and this is where the supercomputing center is located in Offenbach, just in the same building we are located in. Okay, so the Deutscher Wetterdienst is one national service in Europe. There are, of course, like 26 countries, and we have some European organizations, and we have very intense collaboration with them. The EUMETSAT is running satellites For the meteorological applications, it's located in Darmstadt, just half an hour subway from where we live in Frankfurt. And the European Center for Medium Range Weather Forecast is covering the medium range for the weather forecasting in a joint effort of 26 European states. And we, of course, this is funded actually by the National Weather Services, so we fund about 20% of it in Germany. And so we are a national weather service, and what is our main objective? I've put it here: observe, monitor, model, warn, and predict. And there's a law on the weather service, and indeed the law basically puts the warn and predict into the center, but the rest is also important because you can't do this without it. So what does it mean? For example, this is a weather app. DWD is running. This is a nowcasting part of it, and we have this is our global model, the precipitation forecast for the same day, just January 16 here, 7 o'clock in the morning, some screenshots, and you see what the situation was and what the weather model said here as well. And so this is, and then the app, of course, warns, and it gives you more details on this, and this runs 24/7, basically every minute. This is updated. If you go online, you can always download immediately. It automatically downloads the new data and gives this to society, whoever this is. And it is going to a lot of levels of society. It is going to all the fire brigades and all the kind of people sitting there planning their weekend, for example, whether they should be on alarm or not, whether there's a storm coming, whether there's a high precipitation warning somewhere. But it's also going into the flight industry. So every airplane needs a weather forecast, otherwise they are not allowed to take off. So if our supercomputer fails, the whole air traffic in Central Europe is grounded, basically, which is, of course, high impact for various reasons. And also, we are not the only weather service using the data, but I said we develop with 8 countries together, but we also give data to 40 countries worldwide who run their local weather models with our global model. So this goes basically online into 40 countries all the time, what we do with our weather model. And so there's high impact. And at the same time, here, this is now UMETSAT type of pictures. At the same time, we monitor the Earth from space, and we try to make a coherent picture out of the data. So it's not just taking the data and making pictures out of data, but processing the data and putting them into a coherent picture which is in line with all the physical equations and the meteorological understanding of the Earth's atmosphere, of the chemistry of the Earth partly, and of course, land surface processes going on here, ocean processes taking part. And here you see some of the pictures. This is from the Meteosat generations, and there are, of course, programs. It started in 1977, and there are, at the moment, Meteosat's 3rd generation is planned for 20 years, and satellites will come online step by step. And I know the same is, of course, going on in Japan with Himawari and other activities. So we move from simple observations in one channel, like one picture, to hyperspectral observations where you have 16,000 or 30,000 pictures in each column. So 30,000 pictures in every instance at the same time. And you want to take all of them together and generate a coherent picture all the time, basically. So that is the background of all of this. And all these satellites come online in the next 5 years, basically, step by step. I have one slide here to guide you through the framework of numerical weather prediction. So I already mentioned nowcasting. Nowcasting takes the data as they are at the moment and it projects them into the immediate future. Usually one says it's 1 to 2 hours. Yeah? And it takes data only. It doesn't do usually the homogenization, though there are a lot of projects at the moment of data fusion, so they take various data sources and try to combine them. They try to incorporate life cycles. They try to do more. So there's a big movement in this direction, though it's in that community. It's not heavily used at the moment, but it's coming. You have short-range NWP that is trying to make a forecast for the next 6 hours, 12 hours, 24 hours, or 45. Every 3 hours at the moment, moving to every hour at some point in the near future. You have medium-range NWP, making forecasts up to 10 to 14 days where you have real predictability of the atmosphere. And that takes place basically twice a day or every 12 hours approximately. There are some medium range weather models making forecasts every 6 hours. Then you have seasonal prediction, which is a new type of operational service which we run now. And of course, climate projections, giving an idea of how the atmosphere will develop within the next 10 to 100 years. And to do all of this, so we have a global model with a actually mesoscale nest. You need ocean models if you want to do seasonal or medium range weather forecasting. You also need ART models, so aerosols and reactive trace gases intertwined with weather models to be able to do proper forecast for the next days. Then we have limited area modes of models to go to high resolution, convective scale, high precipitation events in the summers, flooding here and there. And it takes place and it's causing a lot of damages and hail. And there's a lot going on in the atmosphere, of course, which has strong impact on economy and on housing and on everything. So, and then here you see the nowcasting with convection life cycles. And here we have the hyperspectral sounder satellite data going into basically all of these retrievals, monitoring, validations for nowcasting, but also for other parts, quality control, and also for climate monitoring. And to do all this here, you also have further remote sensing and in situ measurements, and then data assimilation, inverse modeling, uncertainty, estimation within the weather model. So that's a kind of overall framework. And as a weather service which runs all the regimes, you basically have to take care of all of it. And you have to plan all of it. And that's my point for the whole talk, basically. How do you make sense of all of this in a framework with your supercomputers and your level 2 servers, and how do you do this? So we have one global model covering this part, and we have the nowcasting and short-range NWP, which is another big development strand, line or track here in blue. And we have this NWP nowcasting NWP integration. So further to the background, DWD operates 2 crazy supercomputers at the moment, ranked 99 and 130 on the top 500 list. So not as fast as a K computer, but it's this is a different game, slightly different game, of course, because we have these only for us. And that means one of these computers will run operational programs 24/7. It's there for nothing else. No one else gets access to it. And then there's a second supercomputer basically for development purposes. So we run, and we have a team of approximately 100 scientists altogether who uses the second supercomputer 24/7 and fills it to prepare all the programs which then run on the operational computer. And also it's a backup computer if the operational computer fails for whatever reason. In 30 seconds we can switch to the other one and then run the whole line of developments. And it's a reasonably comfortable situation actually, because when I send a job to this supercomputer, usually 10 seconds later I have it on, which is very nice. If it's not large. If it's large, I have to wait more, of course. So this is an operational framework, and it's very important because this gives the services to the society. And I would even claim that for development, you need to run operational services. So you might think about this because the traditional way to do development is the university tries something out. And this, of course, is important. But if you run something day by day by day, you gain a lot of experiences and insight, which you cannot gain if you just run it once. So there's an interplay between an operational development and a kind of curiosity-driven or peak-driven development in the university business. And I'm in both, so I can see the benefit of both of them, but also how they help each other. Operational NWP. So we run our global model. We run a mesoscale model as a part of the global model. Actually, it's a two-way nested area, so we don't separate this anymore. We don't need a separate data assimilation. I'll show you more in a moment. We have a limited area model. Actually, we also run all in ensemble modes. I come to this in a second as well here. And we run it 24/7. And so this turns around and around and around all the time. Yeah, and it shouldn't stop. And there are further reasons why it shouldn't stop. I also come to this in a moment. So finishing the first part, if you run operational services, you have daily or hourly forecasts, even every 3 hours, every 6 hours. And you can, of course, check the forecasts. Some days later, latest, or some hours later, you can check how good have you been. And so you can monitor your quality all the time, and you can compare your quality, if you have global models, to other global models. And this is what happens all the time. So we are always in an international competition, and there are 14 global centers currently, and there's a top group, and some of them, and here you see, for example, root mean square errors. So the lower, the better. And so you can see where this goes from 2015 to basically now. Pulled this out some days ago. So not everything is there for January yet. But you can see the lower, the better you are. And you see the red curve here is us. And we have been improving by having better, less errors, basically, over time. And this is basically going in with, we put a new data assimilation into operations here, a new model actually in 2015, then our LATKF-based data assimilation in 2016, and then further improvements are going on, which are not as strong. So, but still, we are this is 1,000 meters height, so 850 hectopascal height, and 24 hours lead time, and you see some countries here don't have to look into all the details. European Center has been the best here all the time. They are the world leaders. So they operate on a slightly different time scale. They do medium range weather forecasting. We do the first 3 days as a focus. So we have to deliver earlier, and we don't have that much time to do this. So it's a different game. You see Meteor France, for example, having the same model as ECMWF. They are not as good with their short-range framework as well. So it heavily depends on how you when you have to do your forecast. And, but we are very happy about this. So, okay. So now this was a framework. So now let's look a little bit deeper into what data assimilation is doing and what you need. And then we derive criteria from it. First of all, data assimilation needs an analysis cycle. So we run the model for a short range forecast, 3 hours, for example, globally, or 1 hour for the high resolution mode. Then we do data assimilation. Then we run the model again. Then we do data assimilation. Then we run the model again. So this is called the analysis cycle, and it's needed to do the analysis. You cannot just do it once. If you do just at one point in time a data assimilation, you don't have all the information you need. You basically collect it over time. And there's a spin-up period, which depends on the scale you are working on it. And for global data assimilation, until you have all your information collected, it takes you a month of cycling with all the bias correction algorithms and everything. So, and then you have a forecast shooting loop, and you can do some forecasts at some point. I put in 3 here. But usually this is done twice a day, for example, for the global model. Or it's done hourly or every 3 hours for the regional model at the moment. And then you take from the global model boundary conditions. So you have a global analysis cycle, and you have your regional analysis cycle. Also, this depends on each other. So it's very important. If this doesn't run for whatever reason, you cannot run this one properly. So there's dependencies here all the time. There's, of course, transfer of information, and cycling is crucial. It's an important issue. I'll come back to this later. So we have a global model, 13 kilometers global resolution. So every 13 kilometers, we have a column of points. Over Europe, we have a 6.5 kilometers resolution, a quite large area covering from Iceland to Northern Africa, basically, from the Atlantic, mid-Atlantic to Moscow, to the Ural. And then we have 90 layers here, 70 kilometers height approximately. And here's just some picture, not the best resolution you can do, but just to see something still. And here's the 90 layers, and this is not a regular grid. You basically put points where you need them. And of course, you have higher resolution at the lower part of the atmosphere. And now you get all the data. And I have 3 slides here on data, just as an example. And we have a lot of different data types and sources. And for example, we have these balloons which are launched every 12 hours only in some places. For example, over Europe, think about Germany, 1,000 by 1,000 kilometers size. So you have 100 points here, nearly 80 or yeah, let's say 100 points, but you have only 3 radio zones. So how do you fill all the 100 by 100 points with 3 radio zones? You can't. Yeah, you don't have enough information to fill that. So we will have to use your data non-locally. Come back to this in a moment. Yeah. And then you also have remote sensing, and here you have satellite data. This is in the visible regime every 5 minutes. Here you see airplanes giving you tracks through the atmosphere, so in situ measurements. Now and then, this is an hourly picture here over Europe. You see sometimes during the day you have more airplanes. There's much more. This was just the AMDA protocol. There are different types of data streams coming in. Here you see something going on over the US during the day. You have buoys. You have this is Thames. This is the Thames. This is the ships and land and ship synops. And so the synops are only at the lower part of the atmosphere. And then you have satellite data. This is a geostationary satellite. So this is a disk. The Severi instrument sees. Severi has 8 channels, but it gives you a picture of 8 channels every 5 minutes if you have a rapid scan, or every 15 minutes on a regular scan. And it will be replaced soon by an instrument with hyperspectral resolution, so many more. And here you see an example of one channel of a polar orbiting satellite. So approximately one of these, it goes around every 100 minutes and gives you pictures. And here the Severi, Yazi instrument gives you 8,000 channels per column. And this is one of the first hyperspectral sounders, and there will be more coming up very soon. And also, this data type here is not a point measurement. It's in a column, but it gives you a sum of a particular quantity, like temperature or humidity or mixture of both in the column for each of these numbers here, which you see as a point here. So it gives you hyperspectral, but it's non-local. So it's not in a given point in your big grid, but it's kind of collecting a sum of points, a weighted sum over a large part. And there are other parts, like GPS, which I did not put here, which also gives you sums of variables through your grid somewhere. This is very important, of course, because it immediately influences all you can do on your supercomputer. Let's come back to this in a moment.